In this video, we present our paper, CP-SLAM, Collaborative Neural Point-Based SLAM. Inspired by great progress and potential in neural field-based SLAM community, we proposed the first collaborative implicit neural simultaneous localization and mapping system with RGB-D image sequences. CP-SLAM consists of front-end and back-end modules including odometry, loop detection, submap fusion, and global refinement. First, why is the keyframe-centric neural point field? Take the dominant feature grid representation as an example. It is hard to adjust or align the feature grid when the pose is optimized after loop closure or transformed to the global coordinate system for collaborative SLAM. However, neural point field is not limited by geometry. The scene geometry and appearance are encoded in 3D points with per-point neural features, which are also associated with certain keyframes. Further, we build keyframe-centric model and bind each neural point to a keyframe. Keyframe-centric model allows the locations of neural points to be adjusted as poses are optimized. Next, how to decode radiance and density from our neural point field. We divide an image into small patches and incrementally project each central pixel of every patch to its corresponding 3D location. To acquire features anchored on 3D points, a 2D image is fed into an untrained single-layer convolutional neural network. For each sample point we can decode the radiance and density from its neighbor features. During the decoding process, we utilize positional encoding to encode the original neighbor features and relative pose information. Subsequently, under the action of 3 MLP C, G, and U, meaningful density and radiance can be obtained. Depth map and color map can be rendered by calculating depth and radiance expectations along rays. Then, how we perform tracking and mapping through volume rendering. We use rendering difference loss that consists of geometric and photometric part during mapping process. With the first frame, we need to perform a good initialization at a few higher cost to ensure smooth following processing. During tracking process, we backpropagate farther to optimize camera extrinsics while keeping features and MLPs fixed. Considering strong non-convexity of the color map, only the geometry part is included in tracking loss. Now, let's watch a single-agent demo. By employing the aforementioned procedure, we can achieve the single-agent SLAM task and outperform the state-of-the-art methods in both localization and reconstruction. Note that holes in the mesh reconstruction are caused by incomplete scanning of the scene in this dataset. Next, we will describe how to achieve collaboration among multiple RGB-D sequences. For different sequences, keyframes are continuously passed to the pool in the central server while sequential tracking and mapping in order to find co-visible connections. For each keyframe in the submap, we associate it with a descriptor generated by the pre-trained NetVLAD model. We use cosine similarity between descriptors as the judgment criteria for loop detection. For the pair with the largest overlap, we use it to perform 3D rigid transformation to align submaps. For pairs with decent overlap, we use them as loop edges in the global pose graph optimization. In order to enhance consistency and cooperation, we adopt a new two-stage learning strategy. At first stage, distributed stage, each image sequence is considered as a discrete individual with a unique group of MLPs. At second stage, we expect a common group of MLPs is shared across all sequences. To this end, we iteratively transfer sharing MLPs to each agent for local training and average the local weights as the final result of sharing MLPs, like federated average mechanism. So far, we have successfully developed an entire neural implicit visual SLAM system, CP-SLAM. CP-SLAM is the first collaborative neural implicit SLAM system, which is composed of neural point-based odometry, loop detection, submap fusion, and global refinement. Finally, let's take a look at how the CP-SLAM system accomplishes collaborative exploration in an apartment environment, which demonstrates the superior accuracy and robustness of our proposed system. Through collaboration, more complete scene can be reconstructed with higher efficiency. Thanks for watching.